Hello again. This is the fifth in this lecture series on stochastic processes. Let's just take a look at what we got last time. In the fourth lecture, we were able to evaluate and calculate the probability density function for a wide class of fluctuations with varying memory behavior. And the reason why it's a huge class of stochastic processes is because you have the opportunity to determine or specify the functions f and h and this g to suit the specific physical system that you're trying to study. So explicit forms of the modulating function g and memory function f, as well as the window function h, would depend on the system that you're studying. Now, are there quite a number really of this type of stochastic process? So the question would boil down to how many choices of function f and h are there that you can actually integrate. You have no problem with the function g because it's outside of the integral. Now, if you look at the table of integrals, there's a huge number of combinations of memory function f and this window function h, wherein if you multiply f times h and then you square them and then just like this, you square them and then integrate, they are actually integrable. So you have all these types of combinations as shown in this page, and we have more. So this is a continuation of the listing, and there are many others which we do not include in the list, but this is just to give you a flavor of the combinations of the memory function f and window function h that you can use, which are all integrable. So if you look at here, if you have this integration and that integration, then you have different types of stochastic processes which would fit the particular system that you're studying. Now, when you look at open access data or experiments with a huge number of observable measurements, normally these values would fluctuate. And given this big data, the first thing that you can really do is to get the mean square displacement from this empirical data. And so if you have to match the theory with your experiment, you also must have a theoretical expression for the mean square displacement within this particular framework. So let's try to evaluate and calculate the mean square displacement given this type of probability density function. So, well, just to review, mean square displacement, the bra and ket would represent a mean. So we take the mean of the square of this displacement, the displacement of the fluctuating variable x, its displacement from the mean of x. So you just square whatever is in this round bracket, and you would get this one, and then take the mean. So the mean of the first term is this one, and then the middle term, the cross term, mean of that, and the mean of the last term. So well, in the middle term, the only fluctuating factor there would be the x. So you have twice the mean of x and x. And so this middle term and the last term would subtract from each other. And your final expression would be the mean of x squared minus the mean of x squared. So that means that to get a theoretical expression for the MSD, or mean square displacement, we have to calculate these two objects, these two mathematical objects. So here we have a mean of x, so we have an x here, multiplied by the p, or PDF. And remember that our PDF is actually given by this. And you also have the x squared, mean of x squared. So let's proceed with the calculation. So here, let's first do the mean of x. So I have my x here, and then I just plug in the form of the probability density function. So this would be the coefficient. So the x would be here, and the rest of the terms comes from the PDF. Now, to simplify or make it easy or facilitate our integration, we can have a change of variable. This x minus x naught, I can call that a y, and so dy would just be dx. And this big term here, which does not depend on x, so we can just call that an alpha squared. So if you use this substitution on this big expression, our mean of x would simply look like this. And of course, the x, looking at this substitution, the x would just be given by y plus x naught, as shown by this expression upstairs. So let's look at this expression. So we have this, and so if you distribute the integration, you have two terms, one concerning the y and the other related with x naught. So since the first integral of y times this exponential of e to the minus alpha squared y squared is an even function as you integrate from minus infinity to plus infinity, and it's multiplied with an add function y, which changes sign as you go from minus infinity to plus infinity. So the integration or the summation of all the terms would just give you 0. On the other hand, this is just a Gaussian integral, and so this term here would just give us square root of pi over alpha. So cancellations would happen between square root of pi and alpha, and you're just left with the mean of x is actually your initial point, the starting point of your fluctuations. So we can go to the next term that we need. We have to evaluate mean of x squared. So x squared is in here, multiplied by our probability density function. So this is this big expression here. And to simplify again the expression, we use a substitution. This x minus x naught, we just call that a y, and your dx is substituted by a dy, and this big term here, you just call that alpha squared. So this big expression would become much simpler, and your x squared here is now given by x is just y plus x naught, and then you have to square it. So we proceed, we square that term. So we have this y plus x naught, which is just our x squared. So you square that, you have three terms, y squared plus the middle term plus x naught squared. So you distribute the integration, and you have three terms. You have this, where you can actually apply a relation from Grudstein and Rizik, and you get quickly the first term would just become like this. The second term is again odd and even function as you integrate from minus infinity to infinity, so it would just be 0. And the last term is the same as the one we encountered previously, and which will just give you square root of pi over alpha. So cancellation with regards to square root of pi, and cancellation with alpha, and you're left with just x naught squared, which we put in here. So now we substitute back the alpha squared, and so we're done. Our mean of x squared is given by the initial point squared times this function's g integration of fh squared. So now we can go back to our original expression for the mean. Our mean of x squared is given by this, and our mean of x is just x naught. So you plug in this two expressions in here, and you will see that the x naught would cancel with this x naught, and we are left with a mean square displacement, which is just given by this functions g, f, and h, which at this level, and even at the level of PDF, we have not yet specified. And as I have mentioned, the specification of functions g, f, and h would depend on the system, physical system that you are investigating. And so given this form of the mean square displacement, our first observation is the following. Observe that the probability density function that we have is of this form, and given the mean square displacement that we have calculated, you would recognize that we can use this expression for the mean square displacement and use it in our PDF. And if you do that, we can write our probability density function in this form, in this much simpler form. So you would notice that we are actually dealing here with a wide class of non-Markovian Gaussian processes. It is non-Markovian because the MSD contains a memory function. Okay, this f function of final time t minus t is a memory function. So it is non-Markovian. On the other hand, given looking at the form of the PDF, it is a Gaussian stochastic process. So if you would like to know what is the diffusion equation or modification of the diffusion equation that this framework has, then we can easily do that. In fact, obtain the modified diffusion equation. So with this form of the probability density function, it is straightforward to show that the PDF obeys this modified diffusion equation, where the MSD, you have to take the time derivative of MSD. Here we have used the tau replacing the capital T that we have been used as our notation in the previous pages. And you can easily prove that this is true. And so now the MSD is crucial when you want to apply this to some big data. Normally, when you're again faced with a big data, the first thing that you could do is just from the available empirical data, plug it into your computer, into your program, and generate an MSD. That's your empirical. Now you have to match that empirical mean square displacement with your theoretical MSD, and that would actually help you determine the form of your G, F, and H. So the only crucial part is really an F and H, which is integrable, which should satisfy this integration. And we have seen at the beginning of the lecture that there are a huge number of functions F and H that could satisfy, that are integrable, square integrable. So let's have a couple of examples. Of course, you can easily get the ordinary Brownian motion from here by choosing function g and h equal to 1, and your f as some constant square root of 2d, where d is a diffusion coefficient. But let's look at this. One example that we can view is letting the functions g and h be equal to 1 and your memory function to be of this form. We have encountered this previously in the previous lectures, and this type of substitutions of g, h, and f is of course integrable, and you can do the time integration, and it would give you the expected form for fractional Brownian motion, where the alpha here is actually equal to 2h, where h is the Hurst exponent and the c is just some constant for a given value of h. Now, if you do a log-log plot of this mean square displacement, so log MSD on the left is equal to log of whatever is on the right, then it will just give you an equation of a straight line, where the slope of the straight line is given by 2h. And since h can vary between 0 and 1, then the slope could also of your straight line could also vary. And we have noted last time that for h less than 1/2 or 0.5, it gives you a subdiffusion log-log plot. And for h greater than 1/2 or 0.5, you would have a super diffusion. But the framework that we have here, because of the freedom that we have in choosing the functions g, memory function f, and h, because of this freedom, we can actually go beyond, much beyond fractional Brownian motion. And let's just give one example before we end this lecture. Suppose we choose a combination where g is just equal to 1, a memory function which is given by this, and an h which is t to a certain power times an exponential. And since this combination is integrable, your MSD, looking at the table of integrals, would be given by this. Gamma is just the gamma function. Your I would be the modified Bessel function of the first kind, t to a certain power and some exponential. And if you do a log-log graph of MSD versus your time t, then it will give you this nice curve. So it goes beyond the straight line of the fractional Brownian motion. In fact, in this particular example, if you plug in a value of nu, which is equal to 3/4, and then different values of your mu, then for mu equal to 1/2, then you have this dashed line. For mu equal to 1, then you have this solid line in here, the second one. And for mu equal to 0.87, we have the circles in this graph. And so varying the variables, parameters nu and mu will give you the flexibility to match an empirical MSD with your theoretical MSD. And it will lead you on the road to having a theoretical framework for whatever empirical data that we have. And in the next meeting, we'll deal or give you some examples. Thank you again.